Good to see you all again on the channel. Across modern skies, autonomous drones navigate landscapes that shift in complexity and scale. Behind their precise movement lies a quiet yet powerful computational method, the A-star algorithm. This foundational approach to path planning enables drones to interpret their surroundings, avoid obstacles, conserve energy, and reach their destinations with remarkable accuracy. In this segment, we examine how A-star became one of the most trusted algorithms in autonomous navigation and why it continues to shape the evolution of drone simulation today. Path planning is at the heart of how unmanned aerial vehicles, or UAVs, navigate from one point to another without crashing or wasting energy. For a drone, this means understanding the environment, mapping out where it can fly, searching for the most efficient route, and making sure the path fits its flight limits and dynamics. In real-world drone navigation, we typically rely on two layers of planning: a global planner, such as the A-star algorithm, to create the overall route, and a local planner or reactive controller to make quick adjustments whenever the drone encounters unexpected obstacles or changes in its surroundings. At its core, the A-star algorithm works by trying to minimize a simple evaluation function to find the best possible path. The first part of that function, GN, tracks the cost of getting from the start to the current node. This can include things like the actual distance traveled, estimated energy usage, how close the drone is flying to obstacles, and even expected wind or turbulence along the way. The second part, HN, is a heuristic, basically an educated guess about how much it will cost to reach the goal from where you are now. For A-star to stay reliable, this heuristic has to be conservative. It can't overestimate the true cost, and it has to follow the triangle inequality. That's why common options like Manhattan, Euclidean, or octile distances work so well. A-star is considered optimal when these conditions hold. If the heuristic is admissible and all movement costs are non-negative, the algorithm is guaranteed to return the shortest valid path. The A-star algorithm follows a simple but powerful workflow. It starts by placing the initial node into the open list. Then, at each step, it picks the node with the lowest FN, the one that currently looks most promising. If that node happens to be the goal, A-star immediately reconstructs the path and we're done. If not, the algorithm looks at all of that node's neighbors, calculates their new G, H, and F values, and updates the open list with these candidates. During this process, A-star relies on two important lists: the open list, which stores all the nodes waiting to be explored, and always expands the one with the smallest FN first; the closed list, which keeps track of nodes that have already been examined. This cycle continues until A-star finds the optimal route through the search space. In drone simulation, the environment needs to be modeled in a way that accurately reflects the space a UAV will navigate. This is often done using occupancy grids that label regions as free or occupied, probabilistic maps that account for uncertainty, and 3D voxel grids that capture altitude information. Because drones operate fully in 3 dimensions, their search space is far larger than that of ground robots, which makes efficient heuristics and pruning strategies especially important. To build these environments, we rely on several data sources. Light detection and ranging point clouds provide highly accurate 3D scans of the surroundings. RGBD. Cameras deliver depth maps essential for identifying obstacles. Aerial maps, such as satellite or topographic datasets, help construct large-scale terrain models. And finally, simulation platforms like Gazebo, AirSim, and Unity allow us to create controlled virtual worlds for testing drone behavior. When we apply the A-star algorithm to drone path planning, the first step is to break the 3D environment into a grid of nodes, each represented by its X, Y, Z coordinates. How these nodes connect to one another depends on the drone's motion model, essentially, how the drone is allowed to move through space. Next comes cost modeling, which plays a major role in shaping the final path. These costs can include penalties for flying over elevated terrain, estimated fuel or energy usage, risk levels based on how close the drone is to obstacles, and even environmental factors such as wind or weather disturbances. Together, these elements help A-Star compute a route that is not just collision-free, but also efficient and safe. The raw paths generated by A-Star often have sharp, step-like movements that aren't suitable for real drone flight. That's why post-processing is essential. It smooths these discrete waypoints into continuous, realistic flight trajectories. One common method is using Bezier curves, which create smooth polynomial transitions and are favored in real-time UAV applications because they're both stable and computationally efficient. Another option is B-splines, which offer flexible control over curve shaping. We also have gradient-based techniques, which refine the path by mathematically optimizing its curvature. Finally, the elastic band approach treats the path like a deformable model, allowing it to stretch and adjust around obstacles. All of these smoothing methods help drones move more naturally, reducing motor strain, vibration, energy consumption, and sudden directional changes during flight. In real-world operations, drones often fly through environments that are constantly changing. They may encounter moving obstacles, such as birds or other UAVs, sudden wind gusts or turbulence, shifting no-fly zones, or even GPS drift and sensor noise. Because these conditions evolve over time, drones require path planning algorithms that can quickly adapt, capable of re-evaluating and replanning routes in real time while maintaining safety and efficiency. In most drone simulation frameworks, A-Star functions as the global planner, defining the UAV's long-range route. However, real-world flight demands more than a static plan. Local controllers handle rapid adjustments, ensuring stability under changing conditions. This layered control architecture combines global planning, real-time local control, and continuous sensor feedback. A-Star computes the overall trajectory, while local controllers manage motion and refine the path during flight. Common approaches include P, I, D control, model predictive control, potential fields, and vector field methods. These systems are typically validated using platforms such as AirSim, Gazebo with ROS, PX4, and SITL, Unity ML agents, and the MATLAB UAV toolbox. To understand how well A-Star works for drone path planning, researchers look at a few key factors: how long the path is, how smooth the flight looks, how much energy the drone uses, how safely it avoids obstacles, and how fast the algorithm can run. When used with a proper heuristic, A-Star can guarantee an optimal route. Because it works naturally in 3D space, A-Star is a great fit for aerial navigation, and it's efficient enough to support real-time replanning as conditions change. In short, A-Star remains a core algorithm in drone and robotics navigation. When combined with path smoothing, adaptive improvements, and strong local controllers, it enables reliable autonomous flight even in complex, dynamic environments. If you found this helpful, don't forget to like, share, and subscribe. Your support really helps the channel grow.